So, segregated witness. This is an upgrade that came to Bitcoin in 2017. And the idea is to remove the witness data, I mean the signature data, from the transaction itself. We'll look deeply into this today. There are, before SegWit, there were some major problems with Bitcoin. We had one problem called transaction malleability, which means that a transaction ID of a transaction might change while it's being propagated in the network. And we have something called quadratic hashing, which is basically means that signature verification is inefficient. The larger the transaction, the more inefficient the signature verification. And we waste a little bit of bandwidth between full nodes and lightweight wallets. I will show you that too. And script upgrades are hard. If we want to upgrade the scripting language with new operators, for example, that's hard today. But we'll take this one at a time. So first, transaction malleability. This is the main reason, the main motivation for segregated witness. The others are more or less stuff that we do while we do it anyway. So suppose that you have two transactions and you don't have, you can, first of all, you can spend a transaction that's not confirmed yet. So you can have this transaction 2 over here, still waiting to be confirmed. So you might not even have broadcasted this transaction at all, but you can still make transactions that spend outputs from it, like this. So you have transaction 2 and transaction 3 that spends this transaction. Don't worry about the lock time stuff here. Never mind. And don't worry about these numbers here too. These are from chapter 9. So if you want to know what this is, I suggest you read chapter 9. But don't worry about this here. They're unimportant for this discussion. So, and suppose that you have created these two transactions where transaction 3 spends transaction 2. And then you decide to broadcast transaction 2. So you broadcast transaction 2 like this, and this transaction propagates the network, but she's node here is a bad node. She wants to make your life hard. So she takes this transaction and she modifies it in tiny, subtle ways so that the transaction, the effect of the transaction is exactly the same. The signatures, I mean, it spends the same. So this TX2M here, which is malleated or modified version of transaction 2, it spends the exact same outputs as transaction 2, and it sends the coins to the exact same new outputs, and the signatures are still valid, but it's still different in some ways. And you can do that. You could do that before SegWit. Yeah, so suppose that this happens. We will get back to how you can malleate a transaction, but for now, just accept that that's the thing. What happens? Well, suppose that this transaction, the malleated transaction, gets confirmed instead of your intended transaction. What happens then? Well, if this is confirmed, then it means that this will become invalid because this spends the same outputs as this one. So this is trying to spend already spent coins, which makes this transaction invalid. And if this transaction is invalid, it also means that this transaction is invalid because it spends an invalid transaction like this. So this transaction that you intended to publish later is now also invalid. And this could be some kind of smart contract, or it could be a Lightning network channel or something like that. We haven't talked about the Lightning network, but the Lightning network is a payment network on top of Bitcoin, which doesn't use the blockchain for their payments. You just set up a Lightning connection using transactions, and then you can use that connection to send as many tiny payments as you want back and forth without having to wait for confirmation in the blockchain, but still it's trustless. So that's something I would encourage you to look into, the Lightning network. Okay, so this is a major problem, and especially for the Lightning network and the likes. So how would you malleate a transaction? So if you look at the transaction, it looks like this, a very minimal transaction. It has some data in the script sig. And again, don't worry about these Fs here. This is called a sequence number, and they are not part of the signature scripts. So it's a different field in the transaction input. So if we look closer at this signature script, we can see that it contains a signature and a public key. And the signature itself isn't just a raw signature. It is encoded in a certain way. It is encoded with something called DER encoding. And we can just view it as a container format for a signature. Now, the problem with this container format is that it's not canonical. You can write the container in different ways. So if you alternate the container format without changing the actual signature, this signature script will still be valid, right? But the contents of it is different. That's one way. And another way is that there is at least one tiny way you can change the signature itself. You can change the signature itself with some cryptographic tricks without making it invalid. And the third way to malleate a transaction would be to just add some operators to the signature scripts, like opdupe followed by opdrop, which would just, this opdupe would just duplicate this public key on the stack, and opdrop would drop that public key again. So the effect of this signature script would be the same as without this, but the signature script is different still. So these are the three ways you can change a transaction without actually making it invalid. And from a user's perspective, if this is just a simple payment where nothing depends on it, this might be okay. And if this would confirm, the payment would still go through. The payment you intended to do still is performed. So you might not even notice that this is a problem. Okay, but this way of doing transaction malleability is actually already fixed. This is fixed in something called BIP66. I haven't talked much about BIPs, maybe. BIPs is Bitcoin Improvement Proposals, and it's the way to move Bitcoin development forward. The BIPs are specifications or proposals for changes in Bitcoin core. and well, not only in Bitcoin Core, but in Bitcoin in general. So usually when you want to make a change, you propose, first you start to discuss the change with people, maybe on the Bitcoin Core mailing list, or sorry, Bitcoin Dev mailing list or something like that. And then you start formalizing your idea into something called a BIP. And if this BIP gets traction, it might actually get adopted, but there's no, it's just a way to communicate ideas. There's nothing formal about it. It's just a way to communicate ideas, and some BIPs get adopted, some don't. So BIP 66 was one of those that got implemented and adopted, and it required a specific canonical container. So it's called strict DER formatting, strict DER formatting, and it would require one specific way of encoding the signature in the signature scripts. So that's fixed. And the other two here are not fixed before SegWit. There are some relay policies that nodes would follow. So if a transaction comes in and detects that it uses this cryptographic trick here, it won't relay the transaction, but it's still allowed inside blocks. So a miner could still do this before they put the transaction in the block. So this is not foolproof, but it limits the possibility of making this a bit. And the same here, we have relay policies that forbids that a relay policy that refuses to relay transactions whose inputs contain operators like this. So it must only contain push operators, so to speak. So push operators are the one that pushes just data on top of the stack. That's the only operators that's allowed in these relay policies. But still, this is perfectly valid inside a block. So this is how you could malleate a transaction. And the other another big problem that I talked about is the quadratic hashing. I'll try to explain this. This is a bit delicate, but I said in the very early, it was the second day when we talked about chapter 5 and transactions, that when you are about to sign a transaction, you clear the signature scripts, all signature scripts before you sign it. And then you sign all input, then you create signatures for all inputs. And then you add those signatures to the inputs at once. But that's not the whole story. The whole story is that when you are supposed to clean this, and then you do what I just said, you create all signatures and you put the signatures into the inputs. If these two inputs would spend outputs to the same public key, you could then reuse one signature for this input and reuse it on this input. So to avoid signature reuse, you need to make something unique in this message here. This is the message that you sign, right? You make something unique in this message for each input. So the way you do this historically is to copy, before you sign this first input, you copy the pub key script from the spent output, like this, pkhy. This pub key script is copied into the signature script here. And then you make a signature for this message here. And then for the second input, you clear this again, and you copy the pub key script of this output here, of this output that's referenced here. Maybe it's down here somewhere. So you copy the pub key script from this spent output and you put it in here. And then you sign this message as well. So you have to do something unique for each input here. And why do I have this figure here? Yeah, never mind about this. I don't remember why I put it here. It was something very pedagogical, but probably forgot about it. Sorry. Look, a smile. Okay. So this is when you sign the other input. You put the pub key script into the signature script, and then you sign this message here. Okay, so this looks simple and doable, but if you double the number of inputs in a transaction, you also double the number of hashes you need to do, because you need to hash this message once for each signature. But you also double the size of the message to hash. If you double the input, the transaction gets bigger, right? I mean, double the number of inputs, should I say here. If you double the number of inputs, you also double the number of hashes, and you roughly double the size of the message that you are to hash. And this happens both for the signer and for the verifier. And that's the important part, the verifier. Verification of a transaction should be really quick, because every node in the network needs to do this. And you don't want to waste unnecessary resources on verifying for that reason. It should be cheap and easy to verify. So let's have a look at an example. Suppose we have this transaction here with 2 inputs. It would take 1 millisecond to verify this. I mean, this is just a made up number here. Suppose it takes 1 millisecond to verify this. And suppose now that you double the number of inputs and have this instead. So this transaction is roughly twice the size of this transaction. And it's also got double the number of, twice the number of inputs. So this would then take 4 milliseconds. It would quadruple. For every doubling, you would quadruple the time it takes to verify it. And if you double this again, you will get 16 milliseconds. And if you have 1,000 inputs, it would take 4 minutes. So this is a bit of a problem, actually. So 4 minutes is a substantial amount of time. It's nearly half of the expected block time. And this would cause major issues. Okay, so we want to get rid of this ordo n square issue. And then we have the third problem, which is wasted bandwidth for lightweight wallets. So suppose you have this transaction, and when you take the transaction ID of this transaction, this signature script is included in that calculation. So the signature script is included in the message to hash to get the transaction ID. And that is a little bit of a problem, because when a lightweight wallet wants to verify that a transaction is included in a certain block, it needs to hash the transaction to get its transaction ID, and then compare that to one of the hashes in the Merkle proof, like this. So, and as I said before, the lightweight wallets aren't able to verify the signature scripts anyway. Lightweight wallets doesn't have the inputs, the outputs required to verify the signature scripts. So the only thing the lightweight wallet needs the signature script for is to be able to make this verification here. So it would be great if we didn't have to send this signature script to the lightweight wallets. And you might think that this doesn't seem very much, but let's have a look at the table here. And let's see how much data the signature scripts take for typical transactions. So if you have a typical transaction with 2 outputs and 1 input, then the total signature script size is 107 bytes. And the transaction size in total is 224 bytes. So in this case, it would take 47%. And as the number of input grows, this percentage will also grow, of course. And if you have 8 inputs, the signature script percentage is 68%. So it's a substantial amount of data compared to the whole transaction that's made up of signature data. So it would be great if we could remove the signature data so that we don't have to send that data to the lightweight wallet. And script upgrades are hard. This is the 4th problem I'm going to talk about. Really short now. There are a few operations in the current scripting system that are called op-nop1 through op-nop10. So these are 10 operators that are designed to do nothing. So when you run the script and you see an op-nop, you will just take it out and ignore it, do nothing, and continue. And those nops could be repurposed. You could create a soft fork where you redefine a nop in certain ways. And you can read more about that in chapter 9. In chapter 10.1.4, section 10.1.4. But to do that, you would probably need to read chapter 9 first. So I don't talk about that here because we skipped chapter 9. But doing these upgrades through nops is quirky. It's not perfect. And we also have just a limited number of nops. We only have 10 nops, of which I think we have used 2 or 3. I think it's 2 nops that's been repurposed. Maybe 3, I don't know. So yeah, so if you have read chapter 9, I really suggest that you also read section 10.1.4 of today, because this is required for exercise 10.5. Otherwise, you can just skip it. Skip this exercise 10.5. So the solution to all the above to the above problems is segregated witness. And the general idea is that you take the signature scripts, the data that was previously formally in the signature scripts, you take that data out of the signature scripts and you put it in a separate data structure called the witness, like this. So each row here is one witness field and corresponds to the respective input. So this row here corresponds to the first input, and this row here corresponds to the second input. So this is called a witness, and we remove all data from the signature script and put it in the witness. And when we calculate the transaction ID from this transaction, we don't include this witness data here. So it's just this base transaction here. We call this the base transaction, and we call this the witness. And this full transaction, we call it a witness transaction, or just transaction. when we calculate the transaction ID, we do it just as we did before. We calculate it based on the base transaction. And an old node doesn't know anything about the witness. An old node will just see this base transaction. So an old node will get the same transaction ID as a new node. And a new node will just skip the witness when they calculate it. And when I say old and new node, with old node, I mean a non-SegWit node that isn't upgraded yet. And a new node is an upgraded node that knows about SegWit. And along with this change, we also got a new address format in BIP173, which is called Bech32 addresses. And they look something like this. Oops. They look something like this. It starts with BC1Q and then a number of base 32 characters. So this is not base 58, it's base 32. And the cool thing about this address format is that, first of all characters are of the same case, which makes it more suitable for compact QR codes. QR codes can be much more compact if they don't have to encode both upper and lower case. And they are easier to read out verbally because you don't have to say lower M, lower R, upper B, and so on. You just say W, M, R, D, G, Z. So that's easier to read. And the checksum is much better for this class of addresses. For legacy addresses, the ones that started with 1 and contained a lot of base 58 characters, the checksum was 4 bytes. And 4 bytes can encode roughly 4 billion different values. So if you have a typing error in your address, there's 1 in 4 billion chance that the software will not detect that typing error. But with this checksum, it will detect up to 4 errors with 100% certainty. And even if there are more than 4 errors, 5, 6, or 10 errors, it will be detected with a probability of it will failure to detect that with a probability less than 1 in a billion. So it's very safe to use these addresses, more safe than the previous type of addresses. And I encourage you to go in and read BIP 173 if you want to read up on the checksum algorithm. And to be honest, I don't fully understand it. So see that as a challenge. Okay, so suppose now that you want to sell your laptop to Amy. Amy then would want your Bitcoin address so that she can pay you. And you create one of these Bech32 addresses like this. So you create this address and Amy enters it into her wallet, or maybe she scans it. Anyway, she enters it into her wallet. And this is what happens now. You start from the top here. This is Amy's wallet trying to decode this address up here. So we look at them character by character. First, you have BC and 1. And this is the human readable part. This is called the human readable part. The thing up to the first 1, which is a delimiter. and BC stands for Bitcoin, and 1 is the delimiter. And then we have a Q here, which is the witness version. Rather, we will not discuss yet what these are, but you split it up character by character, and then you have the human readable part, and then the data part after the human readable part is translated through this translation table here. These are base 32 characters, and they each represent a number. So Q here, for example, represents 0. So we translate that to a 0. And this 5 here represent 4 plus 16, which is 20, and so on. And then you have these last 6 characters represent a checksum. So this is the checksum, and this is what we call the witness version. So we extract this witness version from this process. So we remember this. That's why it's bold here. We remember this witness version. And then we continue. We take the witness program and we translate this into, these are 5-bit numbers, right? 0 to 31. So we just take the bits and we rearrange them into groups of 8 bits. And then we, and this is our witness program. So this is C8 right here. And here I have written the witness program in hex code. And so from this decoding, we will extract 2 things. We will extract the witness version, and we will extract the witness program. And Amy will now create an output for me. So this is Amy's transaction that she's created, and she sends 0.1 Bitcoin to my witness public key hash. And if we look closer at this pub key script, it will look exactly like this. It starts with a version byte, the witness version, and followed by the witness program. So that's all there is. There are no operators in this output, which seems weird to people. It doesn't even look like a program, but still this is called the witness program. You could say 1 or 2 things about the naming of these things, but this is the way it is. It's called the witness program. And this is the version bytes. And this is the version byte this is how you in the future can upgrade the scripting language. So that's why we have the version here, to facilitate future upgrades. Okay, so this is the output, and Amy publishes this transaction to the peer-to-peer network. And someone who wants, sorry. So this is now confirmed. And now it's, I want to buy a popcorn machine. This is my money. And I want to buy a popcorn machine. So I asked the popcorn machine guy for his address, and he has a SegWit wallet as well. So he gives me a pay to witness public key hash address. So I put that in the output here. But more importantly, what I do with the inputs. So I want to spend this output. So I referenced this output with the transaction ID and the output index. And then I leave the signature script empty. And instead, I put the signature and the public key in this witness. And then I publish this transaction.
And suppose now that some node on the network receives my transaction. They see this, they see my new transaction here, and they want to verify it. So what do? First of all, they will look at the output. And since this is a SegWit enabled node that does this verification, they will recognize this as the pay to witness public key hash pattern. Because if it starts with a 0 byte followed by a 20 byte witness program, it knows that this is the pay to public key hash pattern. And if it encounters this pattern, it will use a specific template to verify this transaction. So it will use the pay to witness public key hash template, which looks like this. And you might recognize this from the old-fashioned pay to public key hash transactions. It's the same script, basically. It is the same script, but in SegWit, this checksig operator is a bit changed. We'll come back to that later. Okay, so this node will take this template and fill it in with the signature will be taken from the first item in the witness field, and the key will be taken from the second item in the witness field, and the public key hash is taken from the witness program. Rather, is the witness program. And then this script here will be run by the verifier. And if this script evaluates to true, it will be valid. Okay. So this resembles pay to public key hash very, very much. But suppose now that an old node receives this transaction. An old node doesn't see the witnesses. They just see the base transaction. And for this node's perspective, this is what we call an anyone can spend output, which means anyone can take the coins from this node's perspective. So the signature script is empty. So what do the old node do? It will start running the script as it always has. It will start with the signature script, which is empty. So there's nothing to do there. And then it will start to run the program in the pub key script, which is first a push of 0 bytes, a 0 byte, which is put on the stack. And then there's a push of a 20 byte or 20 bytes of data, which is also pushed to the stack. And there's nothing more to do. The program area is now empty, which means we have a stack with this big piece of data, these 20 bytes on top of the stack. And the requirement for a successful evaluation of a script is that the top element of the stack is non-zero. And in this case, the top element of the stack is non-zero. So this old node will accept this script. So it will be valid according to this old node. And this is very important to keep compatibility between old and new nodes. We will talk more about that in chapter 11. And if you want to see, BIP 144 is the part of segregated witness that defines how peers talk to each other when they have between old and new nodes, how transactions can be sent so that old nodes understand the transaction and the block. It just specifies how transactions and blocks are communicated between old and new nodes in a compatible way.
Okay, so I said that this transaction propagates the network, and a SegWit enabled node would verify it like this with this pay to witness public key hash template that looks like very much like a pay to public key hash script. And I also explained how an old node that doesn't know about SegWit, how that node would accept this transaction. Can you please mute your microphone, please? Okay, so this transaction is now propagating the network, and it's waiting to be included in a block. And now a miner that knows about SegWit, a SegWit-enabled miner, will take this transaction and include it in a block. And I will show you how this happens. So I still hear a little bit of noise in the background. I'll stop sharing for a moment and see if we can fix that, because it's a bit annoying. No, I can't find everybody seems to be on mute. Okay, I can't hear a noise right now, so maybe it's fixed. So I'll start sharing again. Okay, so now this miner wants to include this transaction in a block, and in this case, it's transaction 2. And if you have a look at this block here, the upper part of this figure is the same as before SegWit. There is no difference between this data structure here or this structure here now than it was before. So it's the same. The only difference is this hash right here in the Coinbase. And this hash is stored in a specific output in the Coinbase. It's a new output. It's not in the reward output. It's in a second output. And that is perfectly valid according to the old rules. You can have as many outputs as you want in the Coinbase. So that's valid too. So a new node, a SegWit node would create this base block here. We call it the base block, which is the part of the block that's consistent with the old rules. But then this SegWit miner does something more. He will take the SegWit transactions, including the witnesses, that is, and create a separate Merkle tree for these transactions like this to get the witness hash root here. And this witness hash root is then concatenated with something called a witness reserve value. I will mention that in the next few slides. But this is a hash that's let's just say it's a constant hash. So you hash this, you concatenate these two hashes, and you get something called a witness commitment, which is stored in the output of the Coinbase transaction. And in that way, this hash up here will commit to the witness commitment, which in turn commits to all the witness transactions down here. Okay, so this is how it would look. This is how the block would look. And the interesting part here is that if you send this base block data to an old node, they will accept this block. Yep, so this is how the block header commits to the full witness transactions. And let's have a look at this witness commitment a little bit more. This is the witness reserved value. I think it was called witness reserved value, right? So this is the Coinbase transaction here. And this is how you would store the witness commitment in the Coinbase output, in one of the Coinbase outputs. So you use an op-return operator with a witness commitment. An op-return is an interesting operator. It is a way to instruct the verifier that this script should fail. If you run into this operator, just fail immediately. And this means that if this operator is, if a full node sees an output with an op-return in it, it means that this output can never be spent because it will fail always. And this means that you don't have to store this output in the UTXO set because it's pointless, because no one can ever spend it. So why keep it in the unspent output set? So this is a way to store, arbitrary data in transactions without bloating the UTXO set. You can read more about that in chapter 9 as well. Okay, so we store the witness commitment in a specific output, in an op-return output like this. You have the witness root hash, which commits to all the witness transactions, and you have this witness reserved value. And this must match a hash in the witness of this transaction. So the Coinbase transaction is also a SegWit transaction. And this witness only has one witness field, and this witness field must contain the witness reserved value. So, and this is used for future upgrades. And the rule, if I'm not mistaken now, the rule here is that this value must be equal to this value here, so that people can, so that nodes can verify, nodes who want to verify this block can take this value and input it here to this concatenation, and concatenate it with the witness root hash that they have calculated themselves, and see that it's in the witness commitment. Okay. So someone creates this block, and an old node will verify this block. This block looks exactly like before. There's nothing new here really. The only thing is this extra output here, which is perfectly valid according to the old nodes, old rules. So this block will be valid. Okay. Now we have talked about pay to witness public key hash outputs. And the same way that we had pay to public key hashes, and how that was restricted to a specific script. Suppose that we want to make something more fancy, as we did with pay to script hash. We can do that in SegWit 2 with something called pay to witness script hash. So pay to witness script hash is SegWit's version of pay to script hash. So suppose again that John, Ellen, and Faisa will run a charity, and they do it with multisig, and the same setup as they used before with a 2 or 3 multisig script. And suppose also that the guy that you paid for the popcorn machine wants to spend his coins to contribute to this organization. And for this to work, the charity needs to give their Bitcoin address to the popcorn guy. So this is how the charity organization would do this, how they would create an address. They have this witness script here. This is called the witness script. It's the same thing as the redeem script for pay-to-script hash, basically. So you have, just think of it as the redeem script, but we call it the witness script. And this would require 2 out of these 3 keys to verify. It would require 2 or 3 signatures. So they take this witness script and they hash it, and out comes a witness script hash. We call this the witness script hash. And then they will construct their address from this. They take the witness version 0 byte, followed by this 256-bit witness script hash. So it would be 00 followed by this big hash here. And then they would encode this using Bech32 to get their pay-to-witness script hash address, which will look like this. So this looks just like the previous address, just like the pay-to-witness public key hash address, but this one is longer because it has a 32-byte witness program instead of a 20-byte witness program. So that's how you can differentiate between them. That's how you can distinguish them by their length. Okay, so they create this witness script hash, and from that they create an address, and they give this address to you. They give this address to the popcorn guy. Sorry, to the popcorn guy. And this is the output that you gave to the popcorn guy, and now popcorn guy wants to spend this output and send his coins to their witness script hash address, to the charity over here. So they spend this output, which is a pay-to-witness public key hash address. So they spend it in the same way that we spent our coins here over here. So it's the same kind of spending here. But the new thing is the output, which is a pay-to-witness script hash output for the charity organization. And this is this transaction is then published on the peer-to-peer network, and eventually it gets confirmed. And at some point, the charity needs to buy some equipment for a shelter, for example. So they want to spend these coins, to spend it on some shelter. So they ask the store for their address, and they give them this address. So they create a new transaction with this output here that pays for the shelter equipment. But the important part here is what's on the input side of this transaction. Again, the charity will leave their input signature script empty and instead put stuff in the witness like this. So you have this dummy 0 that I talked about earlier, which is a bug. And then you have John's signature and Faiza's signature and the witness script. And as you recall, this over here is the witness script. And they publish this transaction. And now it's time to verify this transaction. So this is how, sorry, I need to move. Yeah. So this is how this transaction would be verified. So the first thing a verifier would do is to have a look at the output here. And what they find, and this is of course a SegWit enabled node, a node that's aware of SegWit. So this node would look at the output and find that it's a 0-byte followed by a 32-byte witness program. And this is the pay-to-witness script hash pattern. So if it encounters this pay-to-witness script hash pattern, it will trigger pay-to-witness script hash code to run. So what it does then is that it takes the witness and pushes the data on the stack, and then it will pop the top item here, which is the witness script. And yeah, it will pop this witness script from the stack and hash it and compare it to the witness program in the pay-to-public key, in the pub key script. So it will compare the witness program with the hash of the witness script so that we are actually running the intended program. And then it will pop that witness script and extract it into the program area like this and start running this witness script against the remaining stack. So now this program runs just the way that it used to do for pay-to-script hash. So it's the same procedure here. And if this program runs, evaluates to true, the spending is valid. So there you go. That's pay-to-witness script hash. And let's talk now a little bit about quadratic hashing again. We have only mentioned the problem. We haven't mentioned the solution yet. So as you recall, if you double the number of inputs of a transaction, you also double the number of hashes you need to do, and you also double the size of the message to hash, which makes it an ordo n square algorithm. And you want to reduce that to ordo n only. So this is how we do this in SegWit. Instead of hashing the full transaction multiple times, you hash it only once. You clean all the signature scripts, and you hash it only once to get this intermediate hash. And then for each input, you create a specific message, which is the out point to spend. An out point is a name for a transaction ID plus an index. We call that collectively an out point. So you have the out point, and you add the witness script that for this specific input, and you add the value of the spent output, and you add this intermediate hash here. So this message here is constant in size, regardless of how many inputs you have. And then you sign this message here and put the signature in the witness. So you do this for each of the inputs. So now it's 4 times a constant, which means that we no longer have an ordo n square. We have ordo n because the message to sign is of constant size, regardless of the size of the transaction. And this is a little bit simplified version of how this actually works. You should read in BIP. Oh, I haven't written it down here. Is it? I can't recall actually what BIP. Maybe you can have it as an exercise to find the correct BIP for this. So this is a simplified version of how it works. So you change 4 different operators to use this fix. You have opchecksig, opchecksig verify, opcheck multisig, and opcheck multisig verify. Those 4 operators are updated to use this algorithm instead. So that's a big change in SegWit. And then improve security for offline signing devices. Yeah, so there is one more issue that we haven't mentioned yet. Notice that we add the spent amounts here. I will tell you why, because it's not obvious why we sign for the spent output values. So suppose that you have a very common setup in Bitcoin is that you have an online wallet and an air-gapped wallet or a hardware device. And the online wallet doesn't have any private keys. It just has this XPub, this extended public key, so that you can generate addresses on your online device, and you can monitor your balance and everything, but you can't spend money on your online device, because an online device is a risky piece of machinery. It will easily get hacked and bad things can happen. So you don't always want private keys on your online devices, especially if you store substantial amounts of Bitcoin. So many people use something called a hardware wallet or an air-gapped signing device or an air-gapped laptop that doesn't have contact with any networks. And I'm gonna go back one. No, okay. So to do that, suppose you want to spend coins. Then you go to your online wallet and you create a transaction that spends some of your coins, but you can't sign it yet because the private keys is on the air-gapped laptop. So to sign this transaction, you need to transfer the transaction to the air-gapped laptop. And that can be done by a USB stick, or it can be done through QR codes or some various means. It can be done over a sound system or, yeah. But anyway, so you want to transfer this to the air-gapped device for signing, so that the signing will happen in a secure environment. And this is then what your what your signing device, your air-gapped laptop, will see. It receives a transaction like this, and it can see that the output contains 1 Bitcoin, and but it can't see the outputs this transaction is spending. So the air-gapped laptop will not have any clue on the transaction fee of this transaction. So if the online device is hacked to lie to the air-gapped laptop about the transaction, sorry, one way to do this, to fix this, is to actually tell the air-gapped laptop, along with this transaction, we send with it the outputs that's being spent, or at least we send the output amounts that are being spent to the air-gapped laptop, so that the air-gapped laptop can display to the user, okay, so you are about to sign this transaction with a fee of 0.1 Bitcoin. Do you want to do this? Click OK. Okay. But the problem there is that the online wallet will be able to lie to the air-gapped laptop with this amounts, the input amounts. So, and suppose that this transaction actually pays 0.99 in fees, but it lies to the air-gapped laptop to make it think that it only spends 0.1 Bitcoin. So that's a big problem. If you then sign this transaction on the air-gapped laptop, and then you publish the signed transaction, you will lose your money to transactions fees. So that's the reason why we also send these amounts, because even if you would lie to the air-gapped laptop, the air-gapped laptop would sign those amounts, and if those amounts aren't correct, the signature will not be correct when a verifier verifies that transaction, because the verifier will have the correct amounts when they verify. Okay, I made that unnecessarily long. I'm sorry about that. So when SegWit was deployed, not all wallets were aware of SegWit. All wallets implementations weren't aware of SegWit addresses. So when SegWit was designed, they built this compatibility layer, so to speak. So for an old wallet that doesn't understand SegWit, you could create a pay-to-script hash address that would be a wrapper of a pay-to-witness public key hash address, so to speak. So suppose that you want to sell your popcorn machine to Nina, and Nina doesn't have a SegWit wallet. Sorry. Yeah. You want to sell your popcorn machine to Nina, and Nina doesn't have a SegWit enabled wallet, so you can't give her a SegWit address. You can't give her a Bech32 address because she won't be able to parse it. So what you can do is to create a pay-to-script hash address and give that pay-to-script hash address to Nina. And the thing about this pay-to-script hash address is that the redeem script is just a 0 followed by your pay-to-public key hash witness program. So we'll have a look at that, how that looks. So instead of having this data in the pubkey script, you instead have the script hash in the pubkey script, and as redeem script you have this pay to witness public key hash output. The thing that would otherwise go into a SegWit output now goes into the redeem script instead. And then you have the witness like this. So now you can verify that the redeem script matches this script hash here. And then if the redeem script is the pay to witness public key hash pattern, you will verify this against this the way you would verify a normal pay-to-witness public key hash payment. So let's go through some, let's have summarize the various payment types that we have seen throughout this course. We have seen, there are 6 different payment types, and I will walk this through pretty quickly now. And these are all listed in the book. I think it's from figure 1030 and forwards. So, summary of payment types. this is the normal pay to public key hash, the first address format we encountered. And it has a program, a script in the output, in the pub key script, opdup, op hash 160, pay to public key hash equal verify and checksig. And then you have the signature and the public key in the input spending that output. And these addresses looks like 1 followed by a number of base 58 characters. And then you have the pay to script hash address format, which has a program like this in the output with the script hash here, which must match this redeem script here. And then you have some signatures that should satisfy this redeem script. And these addresses looks like 3 followed by some base 58 characters. And then you have pay to witness public key hash, which is an output consisting only of a 0 byte followed by a 20 byte witness program. And this witness program is a public key hash. And that's verified against this signature here and this public key. And these addresses looks like BC1Q followed by 38, exactly 38 base 32 characters. And then you have pay to witness script hash, which is the SegWit version of pay to script hash. So you have the witness script hash in the output. Well, you have the version byte also, but a 32 byte witness script hash. And then in the witness, you have the witness script, which must match the witness script hash, the witness program. And then you have some input that satisfies this witness script. And these characters, these addresses looks like BC1Q followed by 58 base 32 characters. And it's more, these are more characters than in the pay to witness public key hash address, because the witness program is 32 bytes here, and for the previous address type, it's only 20 bytes. And then you have these horrible wrapped addresses. Pay to witness public key hash wrapped in pay to public key hash, wrapped in pay to script hash. So you have a script hash here, which must match this redeem script. And this redeem script is what a proper pay to witness public key hash would output would look like. So you use this as if it was in the output of the transaction, of the spend transaction. And you verify this against the witness. And these addresses also looks like 3 followed by some base 58 characters, because this is a compatibility layer. And then you have pay to witness script hash wrapped in pay to script hash. So this is the other kind of compatibility. So you layer. So the output is still a pay to script hash address, and the redeem script must match this script hash here. And this witness script hash here must match the witness script down here. And then you have some input that must satisfy this witness script. And these are also 3 addresses. Whew. So we have just a few slides left. So I hope you're not falling asleep, and I will finish this without a break now. I'll just have a look at the time. It's 12:45. So I think we will be able to finish this before lunch, which is good. Start from current slide. Yes. Okay. So there's one more thing. block size, the block size in Bitcoin is limited to 1 million bytes. And that's the way it almost always has been. And there is a limit on the number of signature operations that can be created, that can be done in a block. So it's a limit of 20,000 signature operations. And SegWit increases these limits in a forward compatible way so that old nodes and new nodes still agree that limits are met. So according to the old rules, a block must not be bigger than 1 million bytes. So yeah, a block must not be bigger than 1 million bytes. And in SegWit, there's a new rule that says that the block must not be bigger than 4 million weight units. And weight units is a new concept. And they are calculated differently based on what data we are counting. So if we look just at the base transaction, 1 byte equals 4 weight units. So these 3,000 bytes will equal 12,000 weight units. But if we look at signature data, we count 1 byte as 1 weight units. So 5,000 witness bytes would equal 5,000 weight units. So this block weight here is 17,000 weight units. So we now calculate stuff differently. We give, so for a, if we have a block that doesn't contain any witness transactions, so we only have old transactions in this block, a SegWit node would count exactly as the old nodes, so to speak. I mean, it would still count weight units, but it would be perfectly compatible with this. Maybe we should, yeah. So using this, you can squeeze in more witness data, because the witness data is no longer counted on the witness data is no longer counted on the old rule, because the witness is ripped out of the transactions. So for old nodes, they only count the base block data without the witnesses. So on top of this size here, you can also have witness data. So the effective block size limit is actually increased. So why do we give a discount for witnesses like this? Why aren't witnesses as expensive as base block data? There are a few reasons. First of all, witnesses don't go into the UTXO set. And the UTXO set is often stored in RAM, and RAM is expensive. So since witnesses don't go into the UTXO set, they doesn't have to be as expensive. I mean, and it incentivizes UTXO consolidation, which means that you are incentivized to spend your SegWit outputs. If you have lots and lots of outputs, you are incentivized to spend your coins or make a consolidation transaction, so that you consolidate all your outputs into one or a few outputs instead. And when the witnesses are cheaper, you are more incentivized to do this. If witnesses were expensive, you would maybe refrain more from doing this. And UTXO consolidation is good for the UTXO set. You want the UTXO set small. And also, since witnesses don't have to be sent to lightweight wallets, they don't have to be, we talked about this. So that's one also a reason for having cheaper witnesses. And doing so also increases the effective block size. So let's have a look at how that would look. So if we take a typical block, or if we look at different blocks here and have a look at the ratio between the number of witness bytes divided by the total bytes of the block. If we have 0 witness bytes in the block, the maximum effective total block size will be 1 million bytes. And that's compatible with how it was before. And if we have 10% witness bytes, that would mean that the effective maximum block size would be a little bit more than 1 million bytes. And as the ratio of witness bytes increases, you come up to something like 2.5 megabytes, like this. For if you have 80% witness data, you would have an effective block size of 2.5 million bytes. And then we have the signature operations limit. I will not talk about that because I think we need to wrap up this. It's the same way you count from now on, you count each signature operation as 4 signature operations, and you increase the limit from 20 to 80,000 SIGOPs. But you count SIGOPs in the base block as 4, and you count SIGOPs in witness data as 1 SIGOP. Okay, let's summarize. We created something called segregated witness here, and that is we rip out data. We rip out signature data from the transaction itself and move it into an external data structure that we call the witness. And instead of signing the full transaction when we sign the inputs, instead of using instead of using the full transaction as input to the signing algorithm for each signature, like this, we use a constant sized input to this signing algorithm to get rid of the ordo n square verification issue. And the blocks are organized just as before for the base block, and we add the commitment to the signature data to this to an output in the Coinbase transaction. We commit to the witness transactions in an output of the Coinbase transaction like this. And what I wanted to say about this, I don't know. So an old node would verify this as anyone can spend. This transaction would be perfectly valid on an old node, and a new node that's aware of SegWit will verify the full witness of this transaction. So this was a monster session, I think. But do all exercises of chapter 10 and chapter 10, exercise 10 and 11 might take some reading from the book because I haven't covered all those details. So you'll have to look that up yourselves in the book. And exercise 10.5 is hard for you to solve if you haven't read chapter 9. And if you have read chapter 9, I encourage you to read also 10.1.4 of chapter 10.